publish easy.
Hi, so I want to talk about a very important theorem in computability theory called the recursion theorem. And what does it actually say informally? It says that if you have a computer program, then you can modify it so that it can replicate itself. And you think that's really weird. It's a static program. How can it replicate itself? It's the fact that it can be modified. So what you can do is you can insert several statements in any program whatsoever to obtain its own source code. In programming languages, what you do is you can open the file called the one that the program is in, and then you can obtain the source code that way. But in this sense, we're talking about Turing machines. So these models of computation called Turing machines, and I claim that any Turing machine at all can be modified to obtain its own source code, which is pretty bizarre if you think about it. The way that we're going to prove this is in stages. We're going to build up to showing something called the recursion theorem, and then we will see an application of when the recursion theorem is useful. So let's get started. Okay, so the first part of the proof is we're going to create a function called convert to Turing machine, and all it does is it converts a string, just any old string, into a Turing machine for that string that just prints that singular string only. That's its only job. Is this function is going to take some string and produce a Turing machine that just prints that string only and nothing else, and just stop. And it's actually pretty easy to make, so let's make it. So how are we going to make this? So convert to Turing machine is going to take some input W. And what do we need to do? We need to construct a Turing machine called PW that just prints W and nothing else. And one thing that we should note is that the PW machine could have its own input. What we want to do is ignore its input and just print the string W that the convert thing gets. So the first step here is to construct a Turing machine called PW. So PW is going to get any input. Then its first stage is to erase the tape, then write W down, and then halt. So it's a very, very simple machine. All it does is erases the tape, writes the string down, and stops immediately. And then obviously the convert function, or the machine, or whatever you want to think of it as, is just going to output that particular machine. So the encoding of that machine in whatever encoding scheme that we wish. So what the convert thing is, it's going to get some input on the tape, some input string W, and then it's going to end with a Turing machine that represents printing W itself, and that's it. And that's how the convert to Turing machine function works. How is this going to be used? Well, let's see. Okay, so the goal that we want to establish at this moment is I want to build a Turing machine called self, and its only goal is to print its own description. So I'm going to state this more formally. So self, on any input whatsoever, it's going to ignore its input, and then what's going to be left on the tape is the encoding of self. No matter what the input is, just write down itself. It's reproducing itself in some sense. So this is going to work in stages, well, 2 stages. So we're going to have 2 Turing machines, A and B, and they're going to comprise the self machine. So what is the A machine going to be? It's going to be the resulting machine from before, up here, the PW machine, but specifically for the encoding of B. So I'm going to hard code this to be the machine that just prints the description of B and nothing else. So that's what the A machine is going to be. And it may be reasonable to try to write B as the Turing machine that just prints A, well, the problem here is that we'll have a circular definition. So if we like try to apply A and then try to apply B to have A reproduce itself, and that is the self machine, well, then now we have circular definition, and that's not a good thing. Here's how it's going to work. So B, we're going to write the instructions for. It's going to be given an arbitrary Turing machine. So on input, some arbitrary Turing machine M, which is going to later be B itself. So the first stage is to compute the Turing machine that corresponds to this arbitrary Turing machine M right here. So compute the conversion function, so convert to Turing machine of this encoding. And you may think, well, that's not allowed because the convert machine works with arbitrary strings. It doesn't work with Turing machines. Well, the description of a Turing machine is an arbitrary string. And so we can convert this to a Turing machine that just prints this description. Now, this thing right here, the thing that the machine produces, the resulting machine is going to be different than this thing. That's definitely possible. Importantly, what we're going to do is we're going to combine this result, this thing, with the original Turing machine. Okay, so how is that going to work? So let's call this thing, oh, I don't know, N. Okay, so the N is the result of converting the Turing machine, the description, into a machine that prints the description of M. So the machine N prints the description of M. N prints the description of M, but it itself is its own description. So all we're going to do is we're going to go combine the two. So combine M and N to complete a Turing machine description. And then we're going to print that description. So print that description. So you may think, how does this possibly work? And what we're going to do is we're going to work through why it actually works next. Okay, so here's a schematic of what's going to actually happen. So we have the A machine right here. Oops. And what's going to happen is that the A machine is going to feed into the B machine in a particular way. So the first step is that A runs. A, remember, is this machine that just prints the description of B and nothing else. So the description of B is going to be on the tape at this point. That's all it is right here. One thing to note is that this whole thing right here is the self machine that just prints itself. We haven't actually achieved that at this point because we have the B machine and that's it. We need the A machine here in front of the B part, but we'll eventually get there. Now the machine B runs. So then what's going to happen here? Well, by definition, what it's going to compute is the convert to Turing machine function of the input. Well, the input is this B machine right here, and that's defined to be A. So convert to Turing machine of B is defined to be A. So move over, Sally. The B machine's going to move over, and we're going to have the computed thing right here, which is A, written on the tape. And step 2 of B is to combine these two things. So this B right here was the input. The A is the computed value, which is a computable thing. We can do that. And step 2 is to combine the two. So we're going to remove the barriers and I'm going to join them together. And since the self machine is defined to be A followed by B, this is exactly the self machine, which is pretty dang cool. So here, the self machine ran with whatever input but erased it and was able to write its own description on the tape. How cool is that? What we want to do now is we want to extend this so that any Turing machine computing anything can get its own description at some point written on the tape. And it's very similar to this, but it involves a little bit more steps than this. So let's go ahead and do that. Okay, so this is a little bit complicated to describe what the recursion theorem is, but I'm going to get you through it. So this Turing machine I'm going to call T, that's the arbitrary Turing machine that we don't know necessarily what the behavior is, and we're going to try to simulate that with a different machine. So the T machine is going to compute some function, I'm going to call it T, and in this case is going to take an extra Turing machine as input. So normally it would compute some input and then produce some output, and we don't know necessarily what those are, but here is going to be given some Turing machine in advance. And we can modify any function that we want so that it satisfies a function like this. So for example, we could put a Turing machine that does nothing and then just ignore it. So any function for that matter has an input and output, and we can just ignore this if necessary, but maybe we are going to use it in this case. So this Turing machine is going to be of vital use for us. Note that this is an arbitrary Turing machine being presented as the first input. It's just sigma star, just some arbitrary input. Then what the recursion theorem says is that there exists some Turing machine, I'm going to call R, computing some arbitrary function, so some sigma star to sigma star. The first one is the input, which is going to correspond with the T function, and the output is going to correspond with the T function. And the recursion theorem says for any input that you wish, the output is exactly the same, where you fix the T function to be R specifically. T can potentially take any Turing machine that you wish, but here we're going to fix it to R, and that's the magic of what R is. R is kind of like the self machine from before, but here we're not only going to be able to get our own description, but also compute the same function T also. And so let's actually prove this recursion theorem. Okay, so here's the schematic of how this is going to work. We're going to make a few modifications, but they will all make sense as I get you through them. The A machine, instead of being defined as the P sub description of B machine, we're going to append T onto that. Instead of P sub description of B, I'm going to append T onto that also. This is totally fine because we have the Turing machine T, we have the Turing machine B, as I'm going to do in a sec. It's very similar to the original one. And T we know about, so we can combine them into a combined Turing machine like this. We can just put the two descriptions together, and this machine A just prints that description and nothing else. And that's it. Okay, so the first step is that A runs. So first step, A runs to the store. No. So when it runs, it's going to have the description of B and T written on the tape. The problem is that the T machine has input, remember? It has some input W that it needs to compute its own function with. How is that going to be preserved? Because when the A machine runs, the P machine right here, which is A, erases the tape and writes down BT right there. Well, what are we going to do? We're going to modify it so that the input is preserved, or whatever is on the tape already is preserved. In this particular case, if we happen to have some input, let's say W written on the tape, then what we can do is have W written there and then write down the description of BT. So instead of destroying the tape, we're just going to leave whatever's there on the tape and then write the description down. And so that clearly can be done. There's no problem with that. But how is this going to help us later on? Well, what we need to do is to look at what the B machine does. So remember, the B machine applies that convert to Turing machine function with the contents of the tape. So what's going to happen next? B is going to run. So step 2, B runs and applies that convert to Turing machine function on the contents of the tape. What is the result of that? That is literally what A is. So this is essentially the description of A, remember? Because we have the BT, that's what's being printed right here, but the W is a part of A because that's the input. So here, what are we going to do? We're going to apply the convert to Turing Machine function and append the A to this part right here. So when B runs, we're going to have the description of A on the tape, and we can finagle it in a way so that the A machine, which is computed when computing the convert to Turing Machine function, is going to be inserted right there, which is pretty dang cool. So now we have ABT right here. Well, what we're going to do is this machine is going to be, I'm going to call R. So this ABT machine, I'm going to define as R. That means that we're going to convert ABT to R. Not convert, that's what it's defined to be. I'm just going to write it differently. So here we're going to have R on the tape. Well, then now what's going to happen is we're going to combine all of these things together into an appropriate format in order for T to take over to be able to do its thing. So now this W is going to be moved over here and merged with R. So then now we have a proper Turing machine with an input. So then now this is on the tape, and remember the T function corresponding to the Turing machine called T takes a Turing machine and an input and computes whatever function. So we now hand control over to T, which is the final step. So let T run with the contents of the tape right now, which are R and W. So at any point, T was an arbitrary Turing machine, and what we were able to do is to get its own source code, so to speak, written on the tape. So effectively, this R machine is what's actually running, and that's getting its own source code. But now what we're able to do is compute with this R that's on the tape right now, and we can do whatever we want with it, along with the W, whatever we want with it, which is pretty dang awesome. So what we need to do is to investigate why would anyone go to the trouble of proving this recursion theorem? What advantage does it give us? So what I want to do is, using the recursion theorem, I want to show that the acceptance problem for Turing machines is not decidable in a completely different way that's a lot easier to understand. So let's suppose, kind of like in the actual proof of the acceptance problem being undecidable, we're supposing that this machine H decides ATM. Then what I want to do is I want to make a decider that it will have a logical contradiction in it. So I'm going to build a Turing machine, which is going to get any arbitrary input W, and what it's going to do is it's going to get its own description, which we know we can do with the recursion theorem. So the first step is to obtain own description. And let's call it B, for instance. So this machine is, I'm going to call it B. So what is the second step going to do is I'm going to run this supposed decider H on this machine, and W is a perfectly valid machine, is a perfectly valid input, so we're allowed to do it. So run H on the input B and W, and it must answer yes or no. And so what is the final hat trick? It's to do the opposite of what H says. Why is that useful? Because think about what happens. So B says on input W, let's say that B accepts W. So B accepts W, then that means that right here, the H machine should say yes. But we just did the exact opposite because the B machine was obtained in the first step. So this step and this one must be different from each other because we're doing the opposite. So B's behavior on W must be different than B's behavior on W because of this third step right here. And so that shows that this B machine is a logical contradiction. And so therefore, this problem is not decidable, because if it were, then this machine would not have a logical contradiction. It's a different proof than the usual ATM proof, but it's very, very cool in that you get logical contradictions as a result. Let's do another example. Okay, so let's talk about this problem, which I call the minimization problem for Turing machines. So here, we're given an arbitrary Turing machine here, I'm going to call M. And the question is there a smaller version of the Turing machine that does exactly the same thing? Not only can we show that this is not decidable, it is not recognizable, which is pretty dang awesome. So min-TM is not recognizable. So how in the world would you ever prove this? So you can't apply Rice's theorem to this, and you can't really do a reduction here, although there are ways around that. But we're going to prove that it's not recognizable very quickly using the recursion theorem. So how will we actually do this? So let's say that there is a recognizer. So suppose a recognizer exists for this problem min-TM. And let's call the recognizer, let's say R. So R is a recognizer that doesn't necessarily halt, but if it has a Turing machine in it, and there's a smaller version of this Turing machine that has the same language, then this recognizer should say yes. So what are we going to do here? So I'm going to build a machine that, again, is going to get us a logical contradiction. So I'm going to call it B again. So on input W. So this is just some arbitrary input. Then the first step is I'm going to get the own description again. So I'm going to obtain own description again. And we called the machine B, so we're going to call the description B, obviously. And we can do this, obviously, by the recursion theorem. So what we're going to do is we're going to run this recognizer eventually until we get a machine that is larger than this. So this is of finite size. We can always find a machine that is of larger size. So I'm going to run this recognizer in parallel, because the recognizer might not necessarily halt until some machine is found that has bigger description than B. And there clearly is one, obviously. There's infinitely many. And what we're going to do is output that. So what are we going to do? We're just going to simulate this machine that has bigger description, maybe let's call it C, and simulate it on W. So simulate C on W. So this is a problem. So it obtained the own description right here. So that means that we're going to find a description that's longer than B. And so this C has a longer description than B right here. Why is that a problem? Because C was found via the recognizer for minimum Turing machine, which means that it cannot have a smaller version, a smaller Turing machine for the same language by definition, because the min Turing machine recognizer found it. But the thing is, B and C are identical because they're simulating the same input. Whatever input B gets, that's what C does. It does exactly the same operations because we were able to obtain our own description. So that implies that this recognizer can't exist because it's able to find a Turing machine with a longer description but still have a smaller version that has the same language, contradicting the fact that this thing is a recognizer. And so this recognizer can't exist as a result. Isn't that pretty awesome? So we can prove a lot of different undecidable and not recognizable things very easily just by obtaining our own description and disagreeing with ourselves or getting a logical contradiction or something like that. So hopefully that was interesting. Leave comments down below about the recursion theorem. I'm watching all of them. I appreciate every comment that you guys bring, and I'll see you next time.
That was easy. That was easy. That was easy.